Hello friends, welcome to this video, and today we are going to talk about how to plot AT graph, acceleration time graph. It's again very interesting and it will take us a step ahead towards cracking the one-dimensional motion completely. So AT graph, as the name suggests, acceleration time graph. So let us start. So in the previous video we took an example that v is equal to 2t. So there we got to see that the graph was something like this. Quickly for reference I'll draw it. So it was something like this. So we had points like 0 comma 0, then 1 comma 2, 2 comma 4, 3 comma 6, and so on. So this was my VT graph. Okay, so 2, 4, 6 in meters per second, and this is 1 second, 2 second, and 3 second, and so on. So this is how it goes. Now acceleration is like, it's related to change in velocity as we know it. Acceleration is change in velocity upon the time taken. That's what we know, right? So in this case, what is the change? So let me prepare the table for this particular, where we'll be talking about this particular situation for which we plotted the VT graph, and see how interesting it's gonna be. So 0, 1, 2, 3, let's say 4 also. So 0, speed is 0. At 1 seconds, the magnitude of velocity is gonna be 2, 4, 6, and 8, and like that, right? So from this time to this time means within 1 second, my delta t is 1 second. That means the change in time is 1 second. So how much is the change in velocity? So this becomes final. This is initial. So v final minus v initial is equal to 2 minus 0. And what is the change in time for that particular change in velocity? It's 1 minus 0. So this is 2 meters per second, and this is just 1 second. So what do I have as acceleration over here? Just the ratio of these two. That's it. So acceleration for this particular interval is 2 meters per second square. It's constant. Oh wow. Right. But we cannot conclude constant right over here. We should look at the next interval also. Next interval is of 1 second as well. What is the change in velocity? 2 to 4. So what is final minus initial again? It is 2 meters per second itself. So in this 1 second interval, we are again getting a change in velocity of 2 meters per second. And we are assuming that direction is same. So that's why we are directly calculating it. So for the next interval also, so let's say this is acceleration is 1. For the next interval, it is again 2 meters per second square with the same calculations. So we can prepare a new table between A and T like this, and we can write down the things. So just for time t is equal to 0, we cannot comment anything about that right now because we need an interval. So let's talk about 0 to 1, right? So at 1 second, it was 2 meters per second square. For 2 seconds, after 2 seconds, it's 2 meters per second square again. Now you can look at these values again. So again in the next 1 second, is it gonna be changing same? Yes. So there could be one confusion that how to find for intervals. It is constant, it's quite simple, that's why I'm doing it. So you can look for a smaller time duration, right? From 0 to 0.1. What is the change in velocity? That can be obtained from this particular equation. I'll show you. But this is the table which can help us to plot the graph, and here it is constant. So my acceleration time graph is gonna be very simple. It's gonna be a t over here, and for all the times it's gonna be 2 seconds itself. 2 meters per second square, I'm sorry. So that's gonna be a horizontal line because all the points you will plot for 1 second, 2, for 2 seconds also 2, for 3 seconds also 2. So that's it. So this is how it will go, and this will be the AT graph for the given situation. You can also talk about any other random time. I'll show you. v is equal to 2t, right? Yes. So I'm starting from t is equal to 0 to t is equal to sometime 0.1, let's say. What is the acceleration? So for that we will calculate the velocity. This is ti, so this is vi, 2 into 0, and this is vf, because it's strictly dependent on time that has been given to us, right? So vf is equal to 2 into 0.1. That's gonna give me 0.2 meters per second. So in this process, what is the acceleration? Vf minus vi upon the change in time. That's it. So you will again realize it is 0.2 upon 0.1. Point gets cancelled because we can write 2 by 10 and 1 by 10. So 10 will be removed from the denominator like this, and ultimately it will be 2 meters per second square itself. So this is a wonderful situation, especially for this particular equation. If you change the equation, it could be something else, right? So this is the AT graph for this case. Let's take one more example where the body is at rest. In rest, velocity itself is zero. Velocity never changes. So it's very straightforward case, right? So all the graphs we can plot. Let's say it is at x is equal to 5 meters. So xt, vt and at, all three, quick. See how we are going to get it. Simple, because it's a very simple straightforward case. So we can quickly plot it. So as you can see, xt, vt and at. So x is 5 meters at all the time because it is at rest. So it would be a simple horizontal straight line like this at 5 meters. At all the times, it's exactly at 5 meters. That's it. If it is at rest, the velocity is 0. So at all times, the velocity will be 0. So this is the velocity line which will be touching the x-axis or the time axis. Clear? And for AT graph, the velocity is always constant. It is always 0. So AT graph will also be this. Wow, so simple, isn't it? Next case is a body who is moving with uniform velocity. 10 meters per second? Yes, constant. It's not changing with time, not with distance. So again, three graphs, quick. Let's plot it. X, T, V versus T. So in such graphs, start from the simplest one. So here, whatever is constant, just plot that first. So velocity is constant, right? So that means at all times it will be 10 only. 10 for 1 second, for 2 seconds, for 3 seconds, for all the seconds, like that. And since there is no change in velocity, acceleration will be 0 always. There is no change. So acceleration is grazing this time axis. What about xt, position time? So for that we will need the initial position also. So let's say the initial position was 0. Had it been not non-zero, it could have started from somewhere else. So x is equal to 0 at t is equal to 0. After 1 second, you can prepare the table also. After 1 second, it will be displaced by 10 meters. So 10, 1. After 2 seconds, it will be displaced by 20 meters because the velocity is constant, right? So 10, 20 and so on, like this. It would be a straight line like this. Simply 10 meters and this is 20 meters. That's all. Had it been not at 0 location, had it been something else, let's say it was 5 meters, so your same straight line with the same inclination would have gone like this, but instead of at 1 second, instead of 10, it would have been 15. That's it. So your table itself will change in that case. X versus t will be 0, it's 5, 1. It will be displaced by 10 meters further, that is 15. In 2 seconds, it will be further displaced by 10 meters. So added to 15, 10 more, so it is 25 and so on. So you can see it is 25 right over here. Clear? Thank you.